today. Maybe not. All right, so we're in our last lecture on this chapter 3. We're talking about fin effectiveness, fin efficiency. So we were already introduced to the fin efficiency. Isn't that the symbol eta with the subscript F in the textbook? And what's it defined as? Well, it's a ratio of the actual rate of heat transfer from that fin into the fluid divided by the maximum as if the whole surface of the fin would be at the base temperature. So if the whole surface of the fin was at the base temperature, then theta B, which is T base minus T infinity, or the fluid temperature, and then you have the area, the convection coefficient and the area of that fin. Isn't that equation for Q max? And so this is the actual rate of heat transfer off the fin. We often unravel the definition and we say Q, the actual rate of heat transfer, is the fin efficiency times the H times the area of the fin theta base. Where again, this is the maximum, as if all of the fin surface was at the base temperature. All right, fin effectiveness. Well, the textbook uses epsilon, and they put a subscript F on it for the fin effectiveness. It's also a ratio, numerator, denominator, something over the other. It's a rate of heat transfer to the rate of heat transfer that would exist without the base, or the fin, so that you have a bare base. That's what it is. So this is the Q with the fin, same as what we had already. And then this is what it is without the fin, just the bare base. Well, what would be the equation for that? The convection coefficient, the area of the base, or what was covered up by the fin when it's put there, attached to the base, and then the theta at the base. So let's say this is a rectangular fin, and we had thickness T and width W. The area of the base is T times W. It's basically the same as our conductive area for conduction out through the fin, the constant cross-sectional area fin. If it was a round pin fin, that area base is simply pi d squared over 4. Now, the effectiveness can be greater than 100%. It could be, it's not limited. But if you look at the efficiency, it doesn't make any sense that that would be greater than 100%. Okay? What happens if we have an array of fins? And it's really hard to show in 2D because I really want to sketch that third dimension. So maybe I'll try and just sketch it. Here's a rectangular fin going back. Let's try and do it like this. Okay, attached to a base. But then we have another one that's right below it. And then we have another one, so that you have an array of these fins. And the fluid can go, between them like that, etc. Okay, well, if you have an array of fins, you can definitely have some exposed base. How's that? Which is let me try and do it like in 2D now. Yeah, try and draw it 2D. You can have some convection off of this area right here, as well as off of the fin area. So the total rate of heat transfer is a combination of the exposed base and what comes off of the fin surface. And we have a model for what comes off of the fin surface. It's the efficiency of that single fin, and there's going to be a whole bunch of them, times the area of that single fin, times the theta base. And I left out convection coefficient, didn't I? Isn't that right? All right. Now, the simpler equation is for this heat transfer off of the base that's exposed. Well, you just have the convection coefficient, the area that's exposed to the fluid at the base temperature times theta base. And so this is the total rate of heat transfer off of that an array. Well, we'd like a simple model for that off of the arrayed surface, and it would be something like some overall fin efficiency of that arrayed surface times some convection coefficient times the area total times theta base. Let me just continue to rewrite now the right-hand side. H, AB, theta B, plus eta of one fin, H, area fin, theta B. You can work this out for a whole section or a part of it, like the whole finned array. I think the textbook uses that approach. Or you can work it out for just one symmetry section with one fin in it. Okay, so we can cancel the theta B's. We can cancel the H's. They're the same in all of these coefficients. And now we have some equation for the overall efficiency of that array of fins attached to a surface is equal to, and you can just work this out. Let me do this for a minute. The area total, okay, is the combination of, let me write it up here or over here. Area total is the area for that exposed base plus the area of the fin. If I just work with the symmetry section, maybe I do go in between and go in between, then this area for the base is this right here, that section plus this section. And the area of the fin is all of this, like that. See what I'm struggling with? I was trying to say, this is what the fluid sees that's of the exposed base, and that base is at TB. Then this is all the area that the fluid sees for the fin. And it's not at the same temperature. Okay, so this is a combination of A sub B and A sub F. Here's my A sub F, here's my A sub B. So let me rewrite this equation here. Equal to A sub B, and then we'll have, I'm going to put A to F right there, and A sub F right there. Okay. If I put a minus, if I put plus A sub F and minus A sub F, did I change anything? No. But what is this term right here? That's the area total, isn't it? And then here I'm going to do this. I'm going to put minus the fin efficiency, or do it this way, 1 minus A to F times area fin. A to naught, area total. I'm just doing algebra. I'm packaging it up like the textbook packages this up. So now I have one simple equation for the overall efficiency of that surface. It's equal to the area total divided by area total, bringing this one over. Hey, that's just 1, isn't it? Minus 1 minus the efficiency of each single fin, where I have the area of the fin divided by area total. I have this equation on the next page. Let's look at it on the next page. Here it is as it's typed out in the textbook. So, what do we use the eta for? Some sort of efficiency. We have a subscript F, one fin. That efficiency for that one fin. Somebody says, Oh, what is the equation for that? Well, it's the hyperbolic tangent of ML divided by ML. The hyperbolic tangent of what? What is M? The fin parameter. M is equal to the square root of HP divided by KA. And L is the length. And if you want, you can put L sub C there. What happens if they put an L sub C on it? What does that mean? It's corrected. They're going to use this simple adiabatic tip, a formula, even though it may not be adiabatic tip, it may be convective tip. But they'll have a little correction to it. Okay, that's what this is all about for this efficiency for one fin. All right, then we have, here it is for the overall surface, A to naught. Okay, and now they have AT. What again was AT? The total area that the fluid sees. It's a combination of the fin area and the exposed base area. And then they have a little different than I prefer, but that's okay. We can understand it. What they're doing is they're saying, now I have N number of fins. That's what the big N is. Oh, I have 5 of them, 10 of them, 11 of them, whatever. So then I have to do the whole area for all of those 10 fins or 20 fins. And then I have to have the area for each of those 10 or 20 fins. I prefer to just look at one section with one fin in it, and then I don't have that N. But that's not on your equation sheet, and that's not in your textbook. So, okay. But it's an area ratio. Let's solve this very simple problem. We have airflow. It's at 30 degrees C, and it enters a rectangular 2 millimeter by 8 millimeter channel. So it's flowing in this rectangular passageway. It's entering like that and going through this rectangular passageway. The air enters and it's at 30 degrees C. The walls of that rectangular passageway are all at 45 degrees C. Where are the walls? Just like I was showing here. It's the whole rectangle is an enclosure. So it has some top, some bottom, some right side, and some left side. Okay. And the convection coefficient between the air and the wall is 125 watts per meter squared degree C. The depth of the passage is 10 centimeters. Again, it's hard to show it, but this is the depth in the third dimension, 10 centimeters. Then it's going to come out of that passageway, but the passageway has a depth of 10 centimeters. What is the rate of heat transfer to the air? Simple question. I would like you to calculate that. I'm going to walk around. Here's the answer, 3.75, but you need to show me how you get 3.75 watts. So we want to use the simple rate equation that the rate of heat transfer from the hot wall to the air is given by the convection coefficient, the area, which is where the fluid air is in contact with the wall, times the temperature of the base or the temperature of the wall minus the temperature of the air. A lot of people just wrote delta T. And we know that this is 45 degrees C, this is 30 degrees C. So a lot of people just put 15 degrees C. This was the easy part, the delta T. The H was the easy part. It's this area. And a lot of people are like, okay, I think the area is going to be 8 millimeters, that's this length, times this is 2 millimeters. 8 millimeters times 2 millimeters, coming in with millimeter squared. 16, is that the area? NO. Okay, well, what area are we talking about then? The surface area. That's exactly right. So basically, how many people said, I'm going to take a perimeter, which is going to be this length plus that length plus that length plus that length, and multiply it by the depth to get my area? Is that the way? I saw some people back here. You're right? That's the way you thought? So the area is the perimeter times the depth The depth was given to be 10 centimeters. And now the whole thing is that perimeter. Okay, so it's like I go up 2, across 8, down 2, back 8. So it's 2, I don't know if I added symbols for this, but 2 times the 2 millimeter plus the 8 millimeter. That's the perimeter, right? Somebody just says, isn't that 20 millimeter? Isn't that the perimeter? Yep, that's exactly right. 20 millimeter times then the depth of 10 centimeters. And so let's work it out in meters so that it looks clean. 0.020 times 0.1 meters squared. So the area is 0.002 meters squared. So if this is 0.002 meters squared, and then we have the H of 125 watts per meter squared degree C, 15 degrees C. Did people confirm that this gives us the Q of 3.75 watts? Thank you very much. If you can solve that problem, now you can solve a more difficult problem. Let's move forward. A compact heat exchanger, and that compact heat exchanger has a bunch of rectangular passageways through which the air flows. All right? So it has a bunch of rectangular passageways. The deal is they have a heat source over here on this side to keep this side all at the constant base temperature. And they have heat source on this side to keep it all at the constant base temperature. So it's symmetrical. Symmetrical about this symmetry line cut right there. Symmetry line. So the question would be, what is the rate of heat transfer from the hot surface to the air in one of those passages? And the challenge is just you say, I know the temperature at this part of the passage, but what's the temperature kind of out in this part of the passage? Isn't it lower? Because that's not where the heat source is. The heat source is over here and over here. So isn't it going to be a little cooler out in this part? Because doesn't it have to conduct and then it's convecting? So guess what? There's my fin. You just discovered a fin in a compact heat exchanger. See that? And so the way you look at it, you say, I want to calculate Q for one of those passages. The passage really has, let's say, this is 1/4. Well, this is one whole fin with the insulated tip. If I just focus on this down here, I have a half of a fin right here, half of a fin because it's symmetrical. Then I have another half of a fin, another half of a fin. But anyway, I have to calculate the overall efficiency of this finned array. I multiply that by the maximum as if the whole thing was at the base temperature. Every piece of the fin surface and base was at the base temperature. We just solved that. 3.75 watts. You can see by the answer right here that this overall thin surface efficiency is very, very, very close to 100%, like 99 something percent. But in another problem, you could have a low thermal conductivity of this material. This K could be low, and it would be maybe 80% or 60% or whatever it is. Let's see, how are we going to calculate the eta naught? It's a finned array. So wouldn't it be 100% minus an area ratio? It's the area that's finned over the total. If you want to put the N in there like the book, fine, but I like to work it out by just one fin. And then we have 1 minus the eta of one single fin. All right? So either I work out the area ratio, area of the fin over area base, which is exposed, plus area fin. That may be easy enough to do. So if we just come in here and focus on it, I know I'm kind of cluttering this up, but I'm going to try it right here. I'm just going to do cut, something like that. So I have this distance right here is S, my spacing between the fins, the fin spacing S, minus the thickness of one of the fins, which is, for this problem, the 2 millimeter, which is reported to be the size of the rectangle passage. It's 2 millimeter. Okay. And then, so it's like, this is the base, 2 millimeter. All right, then what we're going to have, the area of the fin, well, we come out 4 millimeter, come out 4 millimeter. So it's like 8 millimeter. And then what is that? 8 millimeter. Now you can multiply by the W, but the W's cancel, the numerator and denominator. So this turns out to be 8 over 10, 0.8, 80%. Right? So that's what this term right here is in our equation, 0.8. All right, what about the other term that's a lot of work, eta of one fin? Hyperbolic tangent, have we seen that? Of the fin parameter m times L divided by m times L. Somebody looks at this for a long time. It's like I have a fin protruding from the left side and a fin protruding from the right side, and in the middle the two fins butt up to each other. Do I need to use L sub C for this problem? Not at all. Not at all. There's no convection off the tip of the fin. So this L is actually, L is equal to 4 millimeter for this problem. Okay, but what about M? Well, I got to do a little work. M is equal to the square root of H. Now we have a P divided by a K and A. Again, it's like, okay, it's for my fin parameter. What is my P? My P is going to be, you go up T, back W, down T, and over back W, right? So this P, I can't write anymore. Put it over here. P is equal to 2T plus 2W for rectangular fin. All right. And what about my area? My area is the conduction area going out the fin. It's my T times W. You have all those dimensions. You put them in. You have your K and your H in the problem statement. Here's my H. Here's my K in the problem statement. You can calculate the M. Let's see. I calculated the M. And then I calculate M times L. It's not very large. And then I calculate the efficiency, and it comes in at 0.993 or something like that. And then I put the 0.993, and I have this area weighting, and the efficiency overall comes in at 0.994. You might as well just forget that it's even a fin there. You're making a detailed calculation when you could have just assumed that fin is isothermal, and you would have gotten the answer good to 2 significant digits, because when you multiply by 0.994, it bumps it down from 3.75 to 3.73 watts. And so that's the rate of heat transfer into the air for one of those passages. Ready to press forward? We have a 400 millimeter long, 25 millimeter diameter rod. So the total length is 400 millimeters, and the diameter is given to be 25 millimeter. Okay. It has a thermal conductivity K given to be 60 watts per meter C. It protrudes from a furnace where the wall of the furnace is 200 degrees C. So this wall right here is constant temperature, 200 degrees C. All right. It is covered by insulation, so you can see this insulation right here. Now, as a good approximation, you have a highly conductive metal rod sticking out that looks like an iron rod, some steel, versus some pretty good insulation. There's no heat flow through the insulation. Neglect it, right? Just neglect it. It's good insulation. All right, the insulation thickness is 200 millimeters. So guess what the length is protruding after the insulation to the tip of the rod? 200 millimeters. Is this a sketch to scale? No, but there you go. What are they showing about the tip out here of that rod? Insulated. Good. The ambient air temperature is 25 degrees C, and the ambient coefficient of convection coefficient is 15 watts per meter squared degree C. Calculate T naught. This is that temperature of the rod right at the end of the insulation. It's as if you're saying, I don't want a worker to be able to come up there with their fingers and touch it. Well, the worker can't touch it inside the insulation, but maybe the worker could touch it where the rod would be the hottest exposed to a worker to touch or brush up against and possibly get burned. And so you can see this would be a good safety calculation. Give me T naught and I can see if it's too hot, too high, then we have a problem here. A worker may get burned. So there's the theoretical type of background to the problem. The answer is 109 degrees C. How do we solve that problem? There's a lot to organize in this problem. So I would organize my thoughts using what I'm just sketching right there. What does that look like? And this is TW. That's my unknown temperature I want to calculate. And this is T infinity, which is 25 degrees C. This is 200 degrees C. What did I just start to sketch? A thermal network. And we have resistors. And what do we have flowing through it? Well, I don't know the rate of heat transfer through those resistors. But it's like it flows straight through this part, and then it's going to be convected off of the protruding rod and into the fluid. Okay, so this resistance is the easy part. L divided by Ka. It's just one-dimensional through a rod. That L is my L of the insulation. Thermal conductivity in the cross-sectional area. The area is this pi d squared over 4. No problems on that. Now we look, I have to have this resistance for this convection off of a fin into the fluid. It's kind of a combination of conduction through the fin and then convection off into the surface, into the fluid. Well, I know how to write the rate equation. The Q off, from the base into the fluid is equal to the eta F H A delta T, which is T naught minus T infinity. Hey, this is the right delta T that's driving the flow. T naught minus T infinity. What is this H? The convection coefficient. What is this area here? A little tricky. Don't get messed up on area. Is that area pi d squared over 4? No. It's pi d L, isn't it? And this L is L, whatever that is, L naught. What is this term? Fin efficiency, we know how to calculate that. So this whole equation looks like 1 over HA with the modification of the fin efficiency. See? It's like a modified convective resistance for the fin. So we do a little work and we say, okay, eta of F is equal to the hyperbolic tangent of M L naught. Hey, do I put LC or L naught? Look at the tip. L naught. No correction needed on it. Divided by M L naught. I got to get my fin parameter M. Done this a couple times. Square root of HP divided by K. I have my L naught. I calculate the efficiency of that fin. So I calculate that this efficiency comes in at 0.6739. Looks reasonable. So then I can come over here, calculate this overall resistance of convection is 6.2979 degrees C per watt. This conductive through this little stub right here of the rod is 6.7906 degrees C per watt. Those are my two resistances. Just look at the magnitude of both of these numbers. 6.79 versus 6.29. They're close. Guess what this temperature is if you're running out of time on the exam? It's going to be halfway between 225. Right? It's going to be halfway between. So if somebody has a calculator, you say it's going to be 225 divided by 2. You're going to be 112.5. You know what? How far are you off from the right answer? No partial credit. You're doomed, right? No. This would be insightful, and you'd have to explain it. Okay. But anyway, the steps are is you calculate by summing them, because these two resistors are in series, to be 13.088. I could then calculate the Q. Q is equal to the overall delta T divided by the overall equivalent resistance. And we've calculated the Q to be, 13.37 watts. Then we come back to this resistor, and we find that T wall minus T naught divided by the 6.7906 is equal to the 13.37 watts. And you only have one unknown. You can solve for T naught, and you come in right around 109.
Did you do it with it doesn't matter which temperature you use?
You could do it from this other side as well. That's exactly right. I encourage you to do it a couple ways. Build confidence in what you're doing so that you don't trip up on the exam. So with that, I thank you for your attention.